Hey everyone, welcome back. Hope you had a good weekend. We're going to talk about rates of change and direct variation. It kind of goes along with what we did on Friday with slope. Just calling it a different thing now with rates of change because it's more of a situation that we'll use real world. As you kind of go through things, there's more real world examples of rates of change more than slope. One of the most common things that you'll see rates of change with is like pay rate. So a rate of change, like if you're working a job and you're getting paid $7 or not $7, $10 or $11 an hour, that's a rate of change. For every hour you work, your pay is going up $11. So that's what we're talking about when rates of change. We're going to kind of work through trying to figure out rates of change from some graphs and some tables. Again, it builds on what we learned a little bit about on Friday with slope. So let's get started. Another way to call it is direct variation. Direct variation is a relationship between two variables where one is a constant multiple of another. So, like I was saying, rate of pay. The variables are your pay and the number of hours you work. So the relationship is the number of hours you work determines how much you get paid over time. So that's a constant multiple. It's always going to be $11 an hour as you're working through that. So the two quantities show direct variation when y equals kx. That is the formula we're going to use the most, and where k is not a zero. If k equals 0, then we really don't have any direct variation because k times x in that instance would be just 0 because 0 times some number. So k has to be bigger than 0. And then we're talking about k. K is called the constant proportionality. We'll learn as we go through linear equations that it becomes m for the slope. Two quantities show direct variation if one variable is always the product of the other. So it's product of the variable and a number. So $11 an hour is 11 times x. X is our hours. Other phrases that describe direct variation we'll see are varies directly and directly proportional. So a couple other ways we'll see it. And then one way to tell if a relationship is directly proportional is to graph the line. What we're looking for there is if we've graphed the line and the line passes through the origin, then the two variables vary directly, they're directly proportional, it's a constant rate of change. Well, it's always going to be a constant rate of change. But they're going to go through, and we're not adding anything to it then. It's like we're always talking about the rate times the hours, or the rate times whatever x is. If the line doesn't go through the origin, then they're not directly relatable. We're adding something to it, so it's not always going to be the same. Does that make sense? We'll see a couple of examples as we go through this. And here we are. So we're going to graph these lines. We have the point -2, -4, 0, 0, 2, 4. So you'll graph the points on our graph. So I got a point at -2, -4. I got another point at 0, 0, which I already see goes through the origin. So I know right away that these are definitely directly proportional based on our definition. I've plotted a point at the origin, so it has to go through the origin when I draw my line in. There we go with my line. So I see now that yes, they are directly proportional. Does that make sense? We're not adding anything to it. Okay, next one is -1, 0. So I'm plotting -1, 0. I always see right now when I plot x -1, y 0, I'm not through the origin. My next point is 0. When x is 0, y is 1. When y is 1, x is 2. So I see right away that I'm not going through the origin. We've missed our origin in this one. So that tells me we're not directly proportional. If I had to draw an equation of a line here, I'm probably looking at adding some number because if it was 0, that's when we're talking about when x is. When your x value is 0, that's when you're going to be at 0 unless you're adding something or subtracting something to your equation to show the proportionality. So here, not at 0, 0, I'm at 0, 1. So that tells me I'm adding 1 to whatever my rate of change is. Make sense? Okay. So like I said, yes, that goes through. And the next one, no, it does not go through. Okay. So another way to show if two variables are directly proportional is, can we write the equation in, if we were given an equation, can we write it in that y equals x form? If we can get something in just y equals x with nothing at the end of it, or in reality plus 0, then we can say that they're directly proportional. So what we're going to use our inverse operations, where basically the easiest way to say this is we're going to solve for y. So whatever the equation is, we're just going to do everything we need to do that we've been working through to try to solve for y, to get y by itself. So y is going to equal something on the right-hand side. Hopefully that right-hand side looks like y equals kx, then we can say they're directly proportional. If it's not y equals kx, if it's plus or minus anything, then we're going to have non-directly proportional stuff. Okay, it doesn't mean that it's not a function or a linear equation. It just means it's not directly proportional. So here are two examples. We have to decide, are they directly proportional? And then if they are, they want us to indicate what the value of k is. So again, I'm trying to solve for y. So to get y by itself, I have to subtract 4 from both sides. Actually, I think I have this electronically, so hold on for a minute. Erase that. Erase that. Nope, I didn't have that. Okay, so we're trying to solve for y. So I am going to subtract 4 from both sides. I'm left with y equals x minus 4. Again, we're looking for y equals kx. I have kx. My k is 1, even though there's no number there. I'm assuming it's 1, but it's minus something, so this is not directly proportional. Looks like an exclamation point. I don't want it to look like an exclamation point. So the first one is not. Constant or directly proportional. Second one, again, we're solving for y. To get y by itself, I have to divide by 4. So I'm left with y equals, I'm going to change it to 1/4 x. So it's y equals 1/4 x. That looks like y equals kx. My k value in this instance is 1/4. And this is directly proportional. Does that make sense? Everybody see what we're doing there? Because there'll be some problems where we're working with equations. There'll be some problems where we're working with graphs. And there'll be some problems eventually that we're just working with points. But we're going to go through some stuff. Here's some for you to try. I want you to find out from graphing the lines, are they directly proportional? Remember, if they go through the origin, that they are. If they don't go through the origin, they're not. And then we may have to solve an equation for y to find out if they are or not as well. Okay, so go through, enter your answers in Edpuzzle, come back and check what you got. All right, so here's what we should have gotten. The first one, yes, that's directly proportional. It went through the origin. We had a 0.00 as we graphed it. It wasn't in the table, but as we drew our line and connecting the dots, that yes, it went through the origin. The second one did not go through the origin. I can see on the middle point here, -2, 0. So when my y value is 0, my x value is not 0 with -2. So that tells me it's not going through the origin. So that graph there is not directly proportional. We're adding some value to it. Question 3, we're trying to decide, we have to solve for y. I have 1/5 y, so to get y by itself, I'm going to either divide by 1/5 or multiply by 5, whichever is easier for you. I multiplied by 5. So that leaves me with y equals 5x. So yes, they are proportional, and here I forgot to put it as an answer, k equals 5. Again, the next one, it's a little trickier because it's y minus, or x minus y equals 0, so I have to subtract x from both sides. Don't get fooled into thinking that it's still plus 0 and that changes it to not directly proportional because we're adding the 0. So that's why I kind of dropped the 0 off. I don't have anything here. I have just negative y equals negative x. When I divide by -1, I end up with y equals x. The 0 went away because I'm not adding really anything to it. So those are directly proportional. And again, my k value here is 1. Did everybody get that last one? Okay. Here's 4 more for you to work on. Again, we're just looking for equations this time, solving the equations for y. Let me know if they're directly proportional, and then enter your answers in the Edpuzzle and come back and check. All right, so when we did this one here, we got our answers. The first one I had to multiply by y because we were dividing by y. So when I did that, I ended up with y equals x equaled 3y. Then I divided by 3, so I ended up with 1/3 x equals y. So yes, they were directly proportional. That's y equals kx. My k value is 1/3. Number 6, subtracted x from both sides, then divided by -1. I'm left with y equals x minus 12. It's not just kx, it's minus a number, so that's no. They are not directly proportional. Number 7, where you have x on the bottom, so I need to multiply by x to get rid of it on both sides, to get rid of it on the bottom of the left, to get y by itself. I'm left with y equals 9x. So again, k equals 9. Perfect. That's proportional. And then the last one, again, it's another one with a 0 that we're going to be adding 0, so that's just going to fall off. We ended up with y equals 7/8 x, and k is 7/8, and yes, it was directly proportional. Did all that make sense? Okay, going to move on a little bit here. Talk about rates of change, which again, it's just a different word for slope, is all we're doing is we're just calculating slope again. So rate of change is a rate that describes how one variable changes in value related to another. Pretty simple. Rate of change, constant rate of change, that is a rate of change that is constant for all values of x. So it's not changing as we move up. Sometimes you might see graphs and equations kind of go like this. We go down a little bit, then go up. So those are not constant rates of change. Those vary as we go through. You can figure out the rates of change between the different points. I can find out the rate of change between here and here. Same thing, I can find rate of change here and here. But it's not always constant. So when we talk about constant rate of change, that's the one that it's the same all the way through and is graphed as a straight line. Does that make sense? Okay. The rate of change can be both positive or negative. And sometimes we'll have a table or a graph to do it from. So it's either or, a table or a graph. Sometimes you'll get both, but we'll be figuring out both today. First example, we're going to figure it out from a table. So we want to use this table to find the rate of change and explain what it means. So rate of change, yeah, it's great, we can understand, we can calculate it, but what is it actually telling us? How do we know what's going to happen? So from our table, what you'll try to do is pick two values. So I'm going to pick my first one and my second one. What I always do is I'll pick and subtract the higher value, or in this case, I always do the highest x value. So I'm going to do, again, we're looking at for the same kind of as the slope formula. So I'm going to 156 is my two values, minus 78, and that's going to be over 4 minus 2. Because my x is, my bigger x is 4, so I want to put that number first on both the top and the bottom. When I do this math out, I end up with 78 divided by 2, which equals 39. So what this is telling me, if you want to be technical, it's $39. So that's my rate of change. If I wanted to check as a constant, I would then do these two. I would do 6 minus 4, or 234 over 6 minus 4 to see if it was a constant rate of change. Does that make sense? So when I look at this now, it actually is a constant rate of change, just so you know too. So now what it's telling me is I want to explain its meaning. So what is the meaning of that $39? What that meaning is for every computer game you buy, the cost is $39. So if we buy one video game, it's $39. If we buy 10 video games, the cost is $390. If we buy 1,000 video games, the cost is $39,000. We're going up $39 for every extra computer game we buy. Does that make sense? That's what the meaning of the constant rate of change is. Okay, one more example again here. Use the table to find the rate of change, explain its meaning. So we have number of floor tiles used, that's your X, because that's the independent variable. We can use any number of floor tiles, but based on then how many floor tiles we're using, we're getting an area of the floor that's been tiled for our Y value. So again, we're going to pick 2. So I'm going to pick 6 and 3. So I end up with 96 minus 48 over 6 minus 3 equals 48 over 3 equals 16. If you want to check and see if it was constant, you'd have 144 minus 96 divided by 9 minus 6 equals 48 over 3. Same, equals 16. Same, it's a constant rate of change. What does it mean? The constant rate of change is, for every floor tile we use, we can tile, or the area of the floor tiled, we'll call it, I guess, 16 square feet. Don't know what the actual measurements are, but for every tile we use, we're tiling 16 units of the floor. That makes sense. Everybody good? Okay. One last one we'll look at over a graph. Again, this goes back to what we worked on Friday. We're just using rise over run to figure out the constant rate of change. We'll find our leftmost point that we can identify on an XY coordinate. So that's 0, 2. We'll find a second point, 3, 6, and now it's just rise over run. 1, 2, 3, 4. 1, 2, 3. So rise over run is 4 over 3. Again, it looks constant. From our graph, it looks constant because it is the section of the graph we have is a straight line. So we can say that our rate of change here is 4 over 3. Make sense? Everybody good? Okay. One last example, word problem kind of from a chart. Looking at this. First of all, when we look at our graph, we talked about constant rates of change and non-constant rates of change. As you can see here, let me change color so you can see it better on, let's make it a highlighter. So as we kind of see this, our rates of change are changing. Each section of the line is a little bit different slope or steepness than the section before it. So that tells us that we're not looking at a constant rate of change. The rate of change is changing between 2 points on the graph. Does that make sense? So that's what a non-constant rate of change graph would look like. It'd kind of have steep peaks, steep lines, shallow lines, flat lines maybe. So it's not totally constant. So again, we're looking at rates of change. They want us to find the rate of change for these two year periods, 2002, and 2002 to 2004. So again, we just look at our values, we see where they are. They actually telling us the numbers. So from 2000 to 2002, my top numbers are 324 minus 317, and that's going to be divided by 2002 minus 2000, which works out to be 7 over 2, which is 3.5, or 7 over 2. Sometimes you're going to use it as a decimal because it's easier to do. The next one they wanted was between 2004 and 2002, so we'll look at those numbers now. It's 325 minus 324. And then my years are 2004 minus 2002. Here my rate of change is 1 over 2, so 1/2. So everybody see that? So now the question they're asking is, how are the different rates of change shown on the graph? So when we look at the graph, we see that they change by the steepness of the line. So we can say the steepness different. So sometimes you may just be given a graph and say, hey, analyze this. Where is the highest rate of change between 2 points? And you have to find really what the steepest line is. Does that make sense? Okay. Whoops. Practice problem for you from the graph. Take a few minutes to answer the 3 questions. It's calculating rates of change between a period, the first one. Then it's just looking at the graph, where's the bigger rate of change from that first period, and then try to answer that last question. Always enter your answers in the puzzle. All right, so the first one, 2006 to 2008, we find our numbers. We see that they're the red points here, the top 2 points. They tell us what the numbers are. It's 28.73 minus 26.66, 2.07 divided by 2. We get a rate of change of 1.035. Got it, done. Second one, without calculating. They didn't want us to do any numbers. We had numbers, we could have done it. They didn't want us to use them. Find a spot with a greater rate of change. Greater rate of change is a steeper line, so that would be the period between that we can definitely say, yes, it's that period, was 1998 to 2000. And then they're asking, explain which thing it was when the Houston Astros, in this example, built their new stadium. We look and see the rate of change increased. Most baseball teams increase their ticket prices significantly when they build a new baseball stadium. So since the greatest period of rate of change was between 1998 and 2000, we can say that that's when they built their stadium, was between those 2 years. Does that make sense? Everybody good? Okay. Determining whether a function is linear. A linear function, we've already talked about this, is the constant rate of change. The rates of change are constant. We're going to have a linear equation. From a table, it's a little bit more difficult to do. What you have to do to find out if it's a constant rate of change is you have to figure out the rate of change between each group of numbers in the table. What I try to do when I'm doing that is I will look at, say, the first 2 here. So again, it's going to be 15 minus 11 over -2 minus -3. It gives me 4 over 1. So that's telling me it's changing 4. This table is easier because I see my x values are going up 1. That was +1. This is +1. This is +1. This is +1. So my x value is jumping up 1 each time. I look at my y value, +4, +4, +4, +4. So this is constant, which makes it linear. Easier to see as the table's jumping 1 point at a time. Make sense? The second example is a little more difficult because if I look, my x values are going down 3. So when I kind of do this, my x values are going down 3. As they're doing that, my y value is going up 5. Does that make sense? Because I'm going from 11 to 16, so that's +5. I'm going 6 to 11, that's +5. So I can see when I look at it, as long as my changes on the x are all the same, and the changes on the y are all the same, then I can say this is constant. And again, this one will be linear. Does that make sense? So you're going to look at each individual line on the table. What's the change from the line above it? Are those changes constant for both the x and the y? If they are, linear equation. If they're not, nonlinear equation. All right, so 2 for you to try. Find the rate of change between the quantities in each table. Tell me, are they linear or not? And do you answer the netted puzzle? And then come back and check your work. Okay, so I look. I kind of figured it out as 2 there, but now what I really should have been doing is this is +5, +5, +5. This is +12, +12, +12. So my cost is going up plus 12 for every plus 5 change in the values. So I'm good. Make sense? Okay. Second one again, I got plus 2, plus 2, plus 2, minus 40, minus 40, minus 40. So again, I can see my X is going up 2 every time. My Y is going down 40 every time. So again, constant rate of change. I had done that incorrectly when I put the answers in there. So that's what you're looking to do. Again, another one, find the constant rate of change for each linear function and interpret its meaning. So we have heights of plants over time, and then dollars of sales over pounds. Again, take a few minutes, look and see, are they constant? Each one has, because this one has 3 dots you can use. This one here has 2 you can use. You kind of look and see, are they constant or not? So take a look, come back, and check your work. They are both constant, because here we're going up 1 to the right 2, up 1 to the right 2, I'm back on the line, up 1, right 2, I'm back on the line. Constant rate of change. The slope is 1/2. It's a relatively shallow slope on it because it's only going up 1 to the right 2, but again, it's still constant. If we look at the next one, we start at 0, 0. I go up 2 to the right 1, I'm on the line, up 2 to the right 1, I'm on the line, up 2 to the right 1, I'm on the line. Again, constant rate of change, K equals 2, means for every pound of coffee we sell, we get $2 in sales. Everybody make sense on that one? The first one is for every week the plant grows, it grows 1/2 inch. Okay, we're all good? Okay, one last one. Again, take a few minutes, figure it out. I'm not going to make you interpret anything. I just want you to figure out the constant rate of change on this one, see what it looks like, and then come back and check your work. Okay, what you should have found, if you did every single line, it's kind of tricky because we have halves and halves in here. I kind of went right through to the 1 and the 3 because I was pretty confident that it was going to be constant. So for every pound that we increase, the price goes up, or the cost goes up $6.99. If you multiply 6 times $6.99, you will get $41.94. So it is a constant rate of change. So does everybody understand constant rates of change and things like that? There is homework out in classroom, so work on that. We'll do some more stuff tomorrow. I think tomorrow we're going to jump right into now the different forms of linear equations, working with y equals mx plus b first, so you can see how to do that one. Everybody understand? We're all good? All right, I'll talk to everybody tomorrow.